All right, so we'll just go back to the beginning of chapter 8, and we'll start looking at problems. We'll try to do something for each type of problem that will be on the exam. The first slide here has all the details that will be on the test, all that stuff. Yippee. So first question, integrate. This is a reverse chain rule problem. And so what I'm hoping you're noticing is that down here in parentheses we have a linear expression. So whenever we have a linear expression, we can use the reverse chain rule. We could use substitution if we wanted to be super long-winded, but we don't want to do that. We want to be efficient. So the integral here, we take the base. The base is 2x minus 1. So 2x minus 1. We add 1 to the exponent. We divide by the new exponent. So we add 1 and get negative 3. We divide by negative 3. But then we also have to divide by the derivative of the inside. So we're also going to divide by 2. So that will be reverse chain rule. Generally, we like to write things without negative exponents. So we would probably prefer to write it like this. And that 6, if you wanted, could go right in the denominator also. So something like that would be ideal. How's that look? Pretty good? Reverse chain rule. Let's go to negative exponents. So here we have a negative exponent in the denominator. And the technique that we used was to get rid of any negative exponents. So we want to get rid of that negative 4x exponent. So what we did was multiply numerator and denominator by something. We want to multiply by 1. We don't want to change the value. So we want to multiply by 1. And we want to multiply by 1 in a way that it will get rid of that negative exponent. So what will we multiply numerator and denominator by? E to the 4x. E to the 4x will be the factor that will eliminate that negative exponent. So we multiply both the numerator and denominator, knowing that that negative exponent is going to disappear. So that negative exponent, let's see, in the numerator, e to the 4x times e to the 4x. We have exponential expressions with the same base, so we add the exponents. So that's going to be e to the 8x divided by, we distribute, so we'll have an e to the 8x minus 3. E to the 4x times e to the minus 4x is e to the 0, and e to the 0 is 1. Okay, so now we have that, no negative exponents. That's sort of simplified, if you will. Now we have to integrate that. Anyone have an idea?
Isn't that log form?
So it's almost in log form. The derivative of the denominator is the derivative of negative 3 is 0. The derivative of e to the 8x is itself multiplied by 8. So we have to do a little finagling here. We need to have an 8 right there. So now it's in log form. But if we put an 8 in that numerator, we need to multiply the outside by 1/8 to keep the peace. now it is in log form, so we will write our final answer down as 1/8 natural log absolute value of that denominator. Ugh. Anyone have an issue? Question? Complete the square. So we have a trinomial here that's not factorable in the denominator. If that was factorable, we might be able to use a different technique, but if it's not factorable, we definitely have to go with the completing the square technique. And we're focusing on these first two terms. We're trying to complete the square there. So we're trying to build a trinomial that's a perfect square trinomial. We use our technique that says take the coefficient of x, divide by 2 and square. We get a 1. So we need a 1 to complete the square. So we are going to have the following situation. We need a 1, so we're going to borrow 1 from the 50 and be left with 49. Now our trinomial sitting here, that's a perfect square trinomial. So that will factor into x minus 1 quantity squared. So we have the following situation. Got that. And it's really close to being in an inverse tangent form. We're going to factor out that 49 first in the denominator. And when that 49 comes out to the front, it leaves us a 1 in the position to the right. But we also don't have a 49 in this first term, so it introduces a 49 in the denominator. So you can imagine writing a 49 in the numerator and denominator so that you're then factoring out this 49 in the denominator, and then you want to write what's left as a single quantity squared. So we want to factor out those 49s into the bottom, rewrite that as a single square. Now it's in arctan form with reverse chain rule. And we can just write down the answer here. So we're going to have 1 over 49. Let's leave a blank for the reverse chain rule. This is arctangent of whatever is in the parentheses, so arctan of x minus 1 divided by 7. What's the derivative inside those parentheses? 1/7. Divide by 1/7 means multiply by its reciprocal, so we're going to multiply by 7 over 1. And all we can do is simplify that front a little bit, so we get 1/7 times the arctangent of x minus 1 divided by 7 plus c.
Can you also get that from the a squared plus x squared form?
You can absolutely, yeah, if you want to memorize the other form, you can. Definitely. Yep. Other questions? Yeah.
So let's say if it's like we have that complete equation, but we have like a 3x over it, would we separate it into two different integrals, like 3x over that and then 3x over that? Or
So in the numerator, if we had a 3x, just a 3x or a 3 plus x?
3x?
So if it's a 3x, then if this numerator right here were, say, 3x, let's put in a 3x right here, then this is not an inverse tangent anymore. So not an inverse tangent, but what we would do is do trig sub. So we would let tangent equal this, and then we'd figure out what x would have to be. That's one way to do it. Another way to do it, you could do substitution and let u equal x minus 1 over 7, and then you'd have something, you could solve that for x.
So if like on the test, would we ever complete the square like that where we would do trig sub?
I'm not going to put a trig sub with a completed square. Let me think about that.
That's evil.
Yeah, that sounds a little more complicated than I would tend to give you, all in one question. Are you reading that open mic thing? You are?
Yeah. You should come.
Good to you.
Yep. Would it be all right if I?
Yeah, absolutely. Yeah. Yeah, open mic night is always good. So other questions on that? So we can do one that's similar to what Caitlin just said. If we have a numerator, is it obvious that we would not have a direct inverse tangent if there was another x up there in the numerator? Right? We could use trig sub, or maybe regular sub would work. So let's go to parts. The basic rule of thumb for integration by parts is that it's kind of a reverse product rule. And so when we look here, we see two functions. And so it's a natural instinct to go to integration by parts, because integration by parts does allow us to integrate a product. Kind of as a reverse product rule. And when we do integration by parts here, we are going to, we want to pick a u and a dv. And the idea is that we're separating the integrand into two parts. And we generally have a couple of rule of thumbs. Pick the biggest piece, the most complicated piece of the integrand that is easily integrable. E to the 4x is more complicated than x, so that is what we would like to put with the u, dv, and with the u we're going to put the x. The other rule of thumb is if you have a power of x and you put it with u, that's often a good thing, because as you take the derivative in that u column, the power will go down. So this is a pretty natural choice here with those two guidelines. And when we integrate this e to the 4x, we use a reverse chain rule. E to the 4x divided by the derivative of the exponent. So we'll have that. And so now our integral will be u times v, so we'll put 1/4 times x times e to the 4x. So there's our uv minus the integral of v du. So that's going to leave us with the integral of e to the 4x divided by 4 times dx. And this is our crossroads. This is where we look at the new integral, compare it to the old integral, and if it's simpler, we're doing things right. If it's more complicated, go back and switch your u and your dv. Obviously, this is easier. There's no x anymore, so it got simpler. If it gets simpler, you just keep on going. So we'll have our leading term out there. And now we want to integrate e to the 4x. 1/4 obviously is just a constant, just comes along for the ride. To integrate e to the 4x, we get itself divided by the derivative of the exponent, so we're going to end up with minus 1 over 16 times e to the 4x plus c. All good? And then we have our more complicated integration by parts. That's when we do it with a twist. So we should recognize that we're going to have a twist when each of the two functions has derivatives and integrals that kind of don't get simpler. The cosine is going to turn into a sine whether you integrate it or differentiate. E to the x, whether you integrate or differentiate, stays e to the 3x in this case. So neither of those functions is going to simplify with a derivative or an integral. So that kind of gives us a clue that, oh yeah, this is going to be integration by parts with a twist. So with integration by parts with a twist, we're once again going to pick a u and a dv. We just know that we're going to have to do this twice. So for u, it's not going to matter. When you have integration by parts with a twist, it really doesn't matter which you pick for u and which you pick for dv. So to get du, we differentiate using the chain rule. So we'll have that. Integrating, the integral of the cosine function is the sine function. The angle does not change, but then we have a reverse chain rule. So that will be our antiderivative. And if we start the UV process, UV is going to be 1/2 times e to the 3x times sine of 2x. UV minus the integral of the bottom row. So that's going to be 3e, let's see, let's write it as 3/2 e to the 3x multiplied by sine of 2x times dx. And we see that we're going to integrate by parts again. So let's do it again. And there is that cool little shortcut I showed you, or it's not a shortcut, but it's a strategic way. If we want to make things easier, we can push this minus sign to the inside. That'll make our life a little easier. So I'm going to make this a plus out here and put a minus right there. Carter, question?
Isn't the derivative of e to the 3x 1/3 e to the 3x? Or
The integral of e to the 3x. Yeah, with the integral, you divide by the derivative. With a derivative, you multiply by the derivative.
It's new methods of math, guys.
New math. New math. So we're going to do u is equal to, we wanted to use the same strategy we used with our earlier integration by parts. So we're going to use the exponential with the u. And I'm going to leave the constant in there. It just helps keep things neat if we put the constant inside and don't factor it out. If we factor it out, you'll get the right answer. If you don't, screw up the parentheses, but you'll have, big old set of parentheses. So dv is the other part of the integrand, so we're going to use sine 2x dx for dv. We'll differentiate over here to get du. So that will be minus 9/2 e to the 3x dx. And we integrate over here, so we'll get minus cosine 2x divided by 2. Everyone okay with that? So let's go with our naming convention. We called this omega while we were doing it, so let's go ahead and do that again. So omega is the original integral. we are going to write this as 1/2 e to the 3x sine 2x plus u times v. U times v is positive, so that's going to be 3/2 times 1/2 is 3/4, positive 3/4. E to the 3x cosine of 2x. So that's uv minus the integral of the bottom row, v du. So that's going to be positive 9/4 e to the 3x cosine 2x. Yeah?
If we pick like e to the 3x to be the dv instead, would it still be the same?
Yes, you'll end up with the exact same answer. That's one nice thing about integration by parts with a twist, is it doesn't matter what you pick for u and what you pick for dv. It'll work out just fine. So usually it's probably better, if you have a harder time integrating trig functions, maybe put the trig function with u so you're differentiating it. You know, differentiating trig functions is easier.
Is that supposed to be a slot?
So remember that integration by parts, the formula, we have a uv minus the integral of v du. So uv is positive minus the integral of v du, and v du is positive because there's two minuses on the bottom row. Yeah, Daniel?
The plus 3/4 is coming from u being negative 3/2 times me, which is negative, so that makes it positive. Okay.
That's right. So we have 3/2 times 1/2, which gives us the 3/4.
Okay.
Yep. And now what we're noticing is that this over here is a multiple of omega. So we will have, on the left, just omega for now. And then we're going to have, on the right, these first couple of terms. And this will be minus 9/4 times omega. So we've created an algebraic equation that we can now solve for omega. So on the left side, we're going to think of this as 4 omega over 4, common denominator of 4. Add the two omegas together. That's going to give us 13/4 omega equals the right-hand side. We'll still have just these first two terms. And one thing to keep in mind at this step is that we have to introduce a constant of integration. As soon as we move that omega to the other side, we need a constant of integration. Omega represents an indefinite integral, and an indefinite integral is always a family of functions, so we need that c. Final step, multiply both sides by 4/13. Austin, question?
Will you mark us down if we forget to put the plus c in that step but add it in the answer?
Probably not. Okay, so multiply both sides by 4/13. 4/13 will give us this, and when we multiply the 4/13 by the constant, we just keep it as a c, even though we know the c's are different.
Because c eats things.
It's like a little Pac-Man. Gobble, gobble, gobble. Gobbles up other constants. Any part of that? Not sure about?
How do we know the e to the 3x times cosine 2x is omega?
Because that's just what we're
More
gonna
sense
call
with
it.
that.
Oh, that's just what we're.
Yeah, we're gonna call it something.
Okay.
Call it any letter you want.
Okay.
Greek
Should be plus D.
plus D plus constant.
Or plus K, because that's what constant is in chemistry.
I didn't put the opposite sign of the cosine is u and everything, so when I got my final answer, the 313 and the 213 was switched. Because that was with the sign.
But your
The other
313, where's your x? Oh no, it's the e to the 3x. Oh, there's your e to the 3. Okay, I see. So 313.
Because it's just.
There's no edges for that.
Right, so it matches exactly.
Yeah.
Yeah,
It's fine if it's, okay.
absolutely. Yeah, that's good. That's perfect. Pear,
Chill.
question?
Breathe.
Yeah, you have to do whatever this did not. Yeah, yeah, so because you want them to match. Yeah, makes sense? All right. All right, we ready for a shell? Shell, let's go. So find the volume of the solid that's generated when the region bounded by e to the negative 4x and the x-axis on the interval 0 to natural log of 6 is rotated around that line. X equals natural log of 6. So obviously, you need to be able to graph exponential functions by now. That shouldn't be an issue. So e to the negative x, if x is 0, you're going right through 1. And it's an exponential decay. So it looks like that. That's e to the negative x, exponential decay.
Does that converge by any chance?
To what?
So would that function have finite area if you were taking an improper integral of it by any chance?
What do y'all think? If we integrate it from 0 to infinity, would that be finite? Does the exponential function approach the x-axis fast enough? Right? Our threshold was 1 over x. If it approaches faster than 1 over x, it's going to have finite area. And an exponential is going to approach faster than 1 over x. So yeah, it will be finite area. If we integrate from 0 to infinity, it will be finite. Truth.
Sorry, a random question.
No, that's a good question. That's a good question. That's not as random as some of your other questions.
Ow.
Oh, snap! Like that negative 1/12 mumbo jumbo that you claimed was proved?
Yeah, Mr. Wolf can show it to you.
It's so fun. Fun stuff. All right, so there is our
It's not
region
mumbo jumbo, I promise you.
that is going to be rotated around the line x equals natural log of 6. So we are rotating around this line. Everyone okay with the region that we're rotating? We're going to rotate it around and create a little bowl with a flat bottom.
I have a question. So if it's rotated around natural log x, wouldn't that just be the same?
It's rotated around log of 6,
Yeah. Sorry.
not natural log x.
Yeah, that's what I'm saying.
Natural log x is not a line.
I said it wrong.
Make sure you're...
So wouldn't that be the exact same as if you rotated it around the x-axis anyway?
Nope. Around the x-axis?
Yeah, because the borders are 0 and natural log 6 anyway.
If you rotate it around the
Sorry,
x-axis,
y-axis.
if you rotate it around the y-axis, you're going to have the volumes are going to be different, right? The volume. If you rotate this around the x-axis, you've got more volume right near the x-axis. If you rotate this around natural log of 6, you've got less volume right near natural log of 6. Those won't be equivalent unless somehow there was symmetry. Like, obviously, if we created a rectangle, yeah, it wouldn't matter which way we rotated it. But if you have a curved boundary, you are not going to get the same volume. You will get two different numbers. Which one's going to be bigger?
X.
Say again? So if we rotate around natural log of 6, we have more area further from the axis of rotation. So that's going to be further away. That's going to create a surplus of volume. If we rotate around the x-axis, we have a smaller chunk out further away. So when it rotates around, it's going to create less volume on the outside. So it'll be more volume with the way it's set up here going around natural log of 6. Everyone see that?
Different shells.
All right, and we're going to use shells. So let's go ahead and draw a vertical element here. So vertical element. This vertical element is at a random x. Should be 100% clear by now that to create a cylinder, your axis of rotation and the element you draw have to be parallel to create a cylinder. Cylinder, aka shell. Then we are going to ask ourselves for the area of a cylindrical shell, area of a cylinder, area of a shell, whatever you want to call it. That's going to be 2 pi r times the height. Everyone okay with that? All right, so if we have a cylinder, 2 pi r is going to be the circumference down there. That's 2 pi r. And then you multiply by the height. That's going to give you the outside area of the cylinder. Okay, so what variable are we going to integrate with respect to? Are we integrating with respect to x? Everyone clear on that? When you look at your element, you have a vertical element. You can imagine its thickness as being dx, so that tells you what you're going to integrate with respect to. So we need to create an area function that has only x's in it, no y's. So we want to have x's. So the radius. The radius is going to be the distance from your element over to the axis of rotation. So there is our radius. Horizontal distance. Anytime we have a horizontal distance, we do the right x minus the left x to get that length. Right x minus left to get the length of it. So the x value at the right end of our radius is natural log of 6. The x value over here, no, it's just x. So natural log of 6 minus x, that is the radius. And then the height is right there. The height is given by the function. So that blue vertical element that we drew, that representative rectangle, the height of that is e to the negative x. So there is our area function. That tells us the area of the shell at x. So then the volume is the integral of the area. We can pull the 2 pi out. And let's do a little distribution in here while we're at it. So we have natural log of 6. That's going to be multiplied by e to the negative x minus x e to the negative x dx. And the limits of integration will be what?
0 to natural log 6.
0 to natural log of 6. There are cylinders for all x values between 0 and natural log of 6. So we're basically finding the area at each of those x values and compiling them. Okay, well, looks like a little integration by parts. Let's first do the first integral. This one we can immediately integrate. That's going to be e to the negative x divided by negative 1. So we're going to have minus natural log of 6 e to the negative x. That's evaluated on the interval 0 to ln 6. There's the first part. We'll do an integration by parts for the second one. We will choose u to be negative x and choose dv to be e to the negative x dx. So du will equal negative dx, and v will equal minus e to the minus x. So we broke it apart, that function and that function. So now we're going to do u times v. That's x e to the minus x, so plus x e to the minus x, minus the integral of v du. V du is the bottom row. That's going to turn positive. We have e to the minus x dx, and then close the bracket. And we need limits of integration on here of 0 and natural log of 6. And we also will put those on this part right here, 0 to ln 6. We'll do all the evaluation at the very end. There's no need to evaluate intermediate step by step. So we'll just wait to the very end. So we now have 2 pi, bracket or parenthesis. And here we'll have minus natural log of 6, e to the minus x, plus x e to the minus x, minus, well, that's going to change to plus. When we integrate here, we're going to get e to the negative x divided by negative 1. So we have all of this. I guess we can use parentheses since we don't have any other grouping symbol. 6. So we'll have that. Yeah.
So that integral of e to negative x.
Yep.
What happens to that minus sign over there?
This one,
Yeah. So it's
when we divide by negative 1, the integral of e to the minus x is itself divided by negative 1.
Yeah. Just talking about like, so it says v is equal to negative e to the negative x.
Mm-hmm.
So is that supposed to be inside there? Or?
So this is uv right here.
Yeah.
So that times that. Oh, then let me see. Stop doing that. Let's see.
That thought was supposed to be plus the integral.
Right. So let's see. We did that. This part came from there. So we're integrating that. So uv is right here. That's positive.
Yeah.
Minus vdu is positive.
Oh, I see.
So that part's going to make this positive inside the
Okay.
integral.
All right, I see.
See it? Dan?
Before we go to the last step that we're on, could we just put negative natural log 6 times e to negative x plus x to e, and then do the integral bar thing?
The evaluation bar?
Yeah, it's evaluation bar.
Yes. We could do that. Yeah, lots of choice. A lot of choice. What do we get when we plug in 0?
Blank.
Let's see. Do we get 0? Let's just double check that we.
Blank.
Yeah, we're not going to get 0. So sometimes we can ignore the 0 because we're going to get 0. We're not going to get 0 here, so we have to do the math. All right, let's do the math. So we'll do the natural log of 6 first. Is everybody seeing that e to the minus ln of 6? Does everybody see that this is 1/6? Is that obvious? 2 ways you could do it. You could say, oh, this is just 1 over e to the natural log of 6. And the e and the ln collapse and you get the 6 in the denominator. Or you could fly that coefficient out in front from out in front, you could fly it up here into the exponent. It's not an inverse, it's a reciprocal. And this would also be 1/6. So a couple of different ways to see it. So then when we come over here for our evaluation, this part right here is 1/6. So we're going to have minus natural log of 6 divided by 6. And then here we're plugging in ln6. So we're going to have ln6. E to the minus ln6 again is 1/6. So we get that. And then we plug it in there, and once again we get e to the minus ln6. E to the minus ln6 is 1/6. So that is where we're at, plugging in the upper limit of integration. Now we plug in 0, and we're subtracting off the antiderivative at 0. Plugging in 0 here gives 1. Plugging in 0 here gives 0. Plugging in 0 here gives 1. So plugging in 0 there, we're subtracting, so this is going to be plus natural log of 6, minus, minus 0, minus 1. Little bit of cancellation. That and that are going to go away. And tiny bit of simplification. We're going to have 1/6 minus 1. That's going to be negative 5/6. And then plus natural log of 6. There is the volume.
You don't have to distribute it.
No, you don't need to do that. If you want to, you can, but. Caitlin?
Well, we have the question first.
Yes.
Because that's evil.
That's not an evil question. That is about, that's pretty.
Wait, so we have a shut, oh, look at that. Now we know.
What?
I said, look at that, now we know a question on the test. It's gonna be a shut.
A question like that.
Put this
Well,
exact
that's like
question.
basically.
Basically the same. Put that exact question. I guarantee you if I put that exact question on a test,
Unless they're still gonna miss it.
what, let's make it, let's do a little,
Knock on wood, everybody.
let's do a little gambling here.
I love it.
So what if I pick an exact question from here and put it on the test? Will you all agree to, if you all get it right, everyone gets it right, you get an A. But if one person misses it, everyone gets a,
No.
everyone gets a minus 10 off their score.
Oh, hell.
That's my Harrison.
I guess now we get like a slap on the wrist.
You subbed.
No!
It doesn't have to be subbed. It doesn't have to be subbed.
About 15. Yeah, about 15. About 15. Yeah, who wants to give someone else control over your destiny?
What if we just don't sleep that night? You know? It's just a bad night.
I don't even want to control my own destiny, dog.
Right?
You're like, maybe if I did that one, I was not gonna.
All right, so here we've got products, product of a trig function and a trig function, sine and cosine. So who can tell us what the rule is when you have a product of sines and cosines? Split it and then convert the larger portion of the split. So if we have an odd power, if an odd power is on one of them, you pull one off, and whatever you leave behind, which will have the higher power, so that will be two cosines left behind, one is going to come off to pair up with the differential, and the cosine squares have to be converted. So that power on sine is not odd or even, so that thing is just, we can't do anything with that. But the power on cosine is odd, so we pull one off and convert the leftovers. Caitlin?
So if both of them are odd, don't we do the one that'll like be easier? Because if there's like 41 and 5, we'll pick
Correct. Yeah, does everyone follow that? If you have sine and cosine and they both have odd powers, you want to convert the smaller one. Right? If you have sine to the 5th and cosine to the 39th, you want to pull one off and convert sine to the 4th, not pull one off and convert cosine to the 40th. Because that would be a lot of work. So we want to, work smarter. All right, so we are going to pull one cosine off of the differential. You can put the 4 all the way out in front if you want. We've sine to the negative 3 halves. We'll just leave that alone. And then we're going to have 2 cosines that we're going to have here. These are called the leftovers, according to Einstein. That was his terminology.
Call me leftovers.
Joking.
Oh, I was like, wait, what?
No. No.
Like, is this more than what?
No, it was. All right, so then we have to convert those leftovers. So we use the Pythagorean theorem to convert those leftovers. And our whole goal, all of this work is set up so that we can use u substitution with u equal to sine. Yes, exactly. Yes, u equals sine of x. So then du is cosine of x dx. Yeah?
For the 1 minus sine squared of x, we use the Pythagorean identity.
Pythagorean identity, sine squared plus cosine squared is 1.
You said theorem, I got confused.
Theorem, identity. Is there a difference?
I thought Pythagorean theorem was the a squared plus b squared plus c squared, and the identity was the trick part. Am I wrong?
Depends on the book.
Oh, okay.
An identity and a
Fair enough.
theorem, whether you call it, it's true for all replacements of the variable.
Okay,
Whether you call that an identity or a theorem,
Gotcha.
it's kind of, sine squared plus cosine squared is always equal to 1 no matter what the angle is.
Gotcha.
Yeah, so you can call it an identity, you can call it a theorem.
It's a law.
It's a rule. Call it a law, call it a rule.
Can't break the law.
All sorts of things. Okay, so then we have 4. So here is the place to do the replacement, to do your substitution. Don't start multiplying all those signs together. Get rid of the sign first. So this will be u to the negative 3 halves multiplied by 1 minus u squared multiplied by du. Beauty. So on the inside we distribute. So we have u to the negative 3 halves minus u to the 1 half du. Now we have the power on a variable. Just use the power rule. Not happy?
No, I had a question.
You can ask a question.
What if, so are you gonna take points if I don't write dx?
Yeah,
What if
I already gave you mulligans on the first test.
What if I just?
I like heaped
take
mulligans
extra
on you.
time? So write dx.
Well, then you're wasting time in other places if you don't have the time to write dx. Yeah, you will lose points for dx this time.
I'm gonna forget it, so.
How many points per dx?
Depends.
Harrison maybe 3, but the
Harrison.
I get all the way down to C if I miss all the dx. Only sometimes. I'm gonna be honest. Okay. I'm gonna have to pull up my.
Okay, so power rule here, we're going to add 1 to the exponent. Add 1, we get negative 1 half. Dividing by negative 1 half means multiplying by negative 2. And then over here, we're going to add 1 to the exponent, getting 3 halves. Dividing by 3 halves means multiplying by 2 over 3. Plus c. Also a point favorite.
How many points will you take off for missing a plus c?
Depends. Just don't do it. Unless you're super curious. You're super curious. All right, so this is going to be
Better grade.
minus 8. And we're going to have the square root of u in the denominator. U is sine of x. So So we're going to have square root of sine x down here. Minus 2/3 multiplied by sine raised to the 3 halves power plus c. There we go.
Why can you distribute 4 to the 2 but not to the 2?
Because I was waiting for someone to pick it up. Thank you.
Could you also write that as cosecant to the 1?
Yeah, and it depends on the book. Some books will never leave a trig function in the bottom. They'll always change it. So you could easily write this as -8 cosecant square root of cosecant. Yeah. Yep.
If I put parentheses around sine of x and had it raised to the 3 halves power, would you mark it wrong?
No.
Okay.
No. That's fine. No, that's nothing like what Harrison's talking about.
He's never gonna hear the end of
I
it.
didn't even use your sub.
I'm
not, I say you know. That's crazy. Listen.
I didn't even use u sub.
And it was done like 6 months
Famous last words. I didn't do you sub.
Yeah.
It's not.
He's doing his alpha sub. Okay.
Actually,
Wait,
wait,
stand
this
up
is
a little bit more.
Sorry.
This way?
Yeah.
All right, so sines and cosines, odd power is the key. Pull one off, convert the leftovers. If the powers are both even on sines and cosines, then you have to power reduce.
Let me scroll down a little bit, sorry.
Is this scrolling down? Is that direction down? So even powers, you have to use power reduction identities. You have your 2 power reduction identities, and you just have to keep using them until you get the power of 1.
You don't provide those, right?
No!
Wait, isn't there one that you do provide?
That's power
The
reduction.
big power reduction, the n one,
Yeah.
but not the sine squared or cosine squared.
No.
Yeah, sine squared and cosine squared, you have to know those ones. All right, thank you. Want another? Here we go. So secants and tangents, the rules are a little different. So secant to an even or tangent to an odd. So this one we could pick either one. So let's think about what we talked about earlier. With secant to an even, you pull off 2 secants and you convert the leftover secants. So if we were to pull off secant squared, we'd be left with secant squared to convert, which is pretty easy because we have a Pythagorean identity. If you pulled off, if tangent is to the odd power, to an odd power, you pull off a sectan and you convert the leftover tans. So if you pull off 1 tan from here, you're left with 4 tans, which is going to be more complicated to convert than 2 secants. So the most efficient way is going to be to pull off the secants. So we're going to leave the tangents alone. So we'll leave our tangent to the 5th of x. We're going to pull off secant squared, which creates a secant squared as leftovers. So we have that. So these ones right here, these are our leftovers. These are the ones that we're going to convert to tangents. And secant squared is 1 plus tan squared. We're going to have tangent to the 5th multiplied by 1 plus tangent squared multiplied by secant squared x dx. And now we're going to let u be tangent. So du is going to be secant squared of x dx. And that's going to unravel very nicely. So we've got that. And that turns right, we'll just distribute the u to the 5th. u to the 5 plus u to the 7 du, power rule. U to the 6 over 6 plus u to the 8 over 8 plus c. And then we just have to go back to tangents. So 7 divided by 6, tangent to the 6. X was our original variable. Plus 7 over 8. Tangent to the 8. And voila. Yeah?
Is it possible to let u equal secant of x for this one?
Yeah, if we go the other way. So if we want to pull off a secant, so the way we just did it, we focused on this. We pulled off secant squared. If we do it the other way, let's set that up. We are going to have 7 integral. We're going to pull off a secant tangent for the differential. And the tangent's going to go down to the 4th. Secant's going to go down to the 3rd. So we have that. Now, we're trying to let u be secant so that that's the derivative of u. So that means we have to convert these leftover tangents. So those are the leftovers. So we want to convert those. So we're going Pythagorean. Tangent squared is secant squared minus 1. So we're going to have secant squared minus 1 quantity squared times secant cubed times sectan. So we've got that. So, any questions in doing it that way? We're going to end up with obviously a slightly different looking answer. So when we go this way, we're going to let u equal tangent. So then du is sec. We're going to let u be secant. So that du is secant tangent. Times dx. So what does that give us? So our new form is going to be 7 integral u squared minus 1 squared times u cubed times du.
That's a lot more ugly.
Yeah. Yeah, if you pick the wrong way, it's definitely more work. So we square this out. We are going to get u to the 4th minus 2u squared plus 1 times u to the 3rd. Then we distribute the u to the 3rd. So we'll have 7 integral u to the 7 minus 2u to the 5th plus u cubed du. Power rule for integration. So we have the 7 in front, and then what do we get? U to the 8 over 8. We get u to the 6 over 3, and then u to the 4th over 4, plus c. So this is very much like the one on the worksheet, which I will have finished. I will finish grading them today after class. So we're going to get 7 secant to the 8th of x divided by 8 minus, what is that, secant to the 6th of x divided by 3 plus secant to the 4th plus c.
And the 7's going to be multiplied throughout.
Oh, did I not multiply it all the way through? Yeah, it should be multiplied through. So that should be 7 over 3 and 7. Thank you. 7 over 4. Yeah. So if you were to graph these two, they look different, obviously. One has tangents, one has secants. If you were to graph both of them, you would see that they just differ by a constant. They would be parallel. And so they're equivalent. If you wanted to be a total crazy loon, you could convert one to the other with the Pythagorean identity. You can turn your tan squares into secant squares minus 1, boil it all out, and get that one. Ooh. Just if you're bored.
But you'll have both answers on your key.
Yeah, both of them are fine. Both are fine. Both are fine. All right, let's take a 10-minute break. Let's take 10. Take 10. So here we only have one choice. The only choice is to go with the secant. The tangent is not raised to an odd power, so there's nothing we can do there. So here we are going to pull off the secant squared. So we're going to have 8. We'll write that as tangent to the 1/2 of x. And then secant squared. So the secant squared that goes there, we're going to replace it with
1 plus tangent squared.
yeah, 1 plus tan squared. And now we're all set for u equals tangent. So when this is to an even power, we split it with secant squared and secant squared. And then that secant squared here gets replaced with 1 plus tan squared. And then we're going to let u equal tangent. And the derivative of tangent,
Thank you so much.
it's going to be secant squared. Yep. So that's exactly why we pulled off secant squared. If we pull off secant squared, it's so that we can let u equal tangent. And then we're going to have 8. This is going to be u to the 1/2 multiplied by 1 plus u squared all times du. And then we'll do a distribution. Distribute this across. So u to the 1/2 plus u to the 5/2 du. And then we can just add 1 to each exponent, divide by the new exponent, so we're using the power rule. So add 1, divide, add 1, and divide. And then we go back, we let u be tangent. So we're going to have 16/3 tangent to the 3/2 of x plus 16/7 tangent to the 7/2 plus c. Any issues?
So the tangent x inside the du equals, can that replace every single tangent?
This, say that once again.
Okay, so where it says du equals tan x, secant x dx? Or,
We're d.
oh, wait, you did it different here, okay.
Derivative of tangent is secant squared.
Oh, never mind. I did u equals secant x.
Yeah, we can't do that here.
Okay, my bad.
Nope. So if we wanted to let u be secant, then we're going to pull a secant tangent off, but that only works if tangent is raised to an odd power. So if secant is to an even power, we pull off 2 secants with the goal of letting u be tangent, so its derivative matches what we pulled off. Whatever we pull off, that needs to be such that the derivative of the other function gives you the du. So if we pull off secant squared, we want to let u be tangent. If we pull off sectan, we want to let u be secant because secant's derivative is sectan. Yep.
Why distribute the 16?
Because we can't factor it out of the c. When we factor out of everything. You don't factor just out of the first 2 terms. Are you following me?
Yeah.
Like if you have x squared plus x plus 1, you don't write this like that. Right? The whole idea of factoring is that you factor it out of the entire expression so that you can then find zeros or something. So just factoring out a part of an expression isn't really helpful. So usually we don't do that. Normally. All right, let's go to your favorite topic, trigonometric substitution.
Substitution.
Trigonometric substitution.
Substitution always
This
works.
is easy. I actually was cheating.
There's another way to do this one, maybe. Okay, so we have 3 trig subs, sine, secant, and tangent. What we would like to have is a difference of squares with a 1. That makes trig sub easier in the long run. And so what we're going to do is factor out that 196. So we factor that out. Square root of 196 is 14. So that's going to be in the denominator. So the 196 came through the square root, so we have to take the square root of it, get 14. We're left with 1 minus. There is no 196 over here, so you can imagine in your head, if you need to, multiplying by 196 over 196. And then the 196 that's factored out are those ones. And then we want to rewrite what's left as a single square. So that's going to be x divided by 14 squared. So there is the algebra. And now, we're good to go. Sine, secant, or tangent? Sine. Because 1 minus sine squared is an identity. 1 minus secant squared is not an identity. All right? Everyone agree with that? If you were to look at the secant tangent identity, tangent is right here, secant is right here, 1 is right there, and 1 minus secant squared, so this tells us that 1 plus tan squared is secant squared. So if you do 1 minus secant squared of theta, that's negative tangent squared of theta. We can't put negative tangent squared underneath the square root because we'd have imaginary results. Right? Only one of them works, sine, secant, or tangent. So we want to do sine because 1 minus sine squared is an identity, not 1 minus secant squared. So we'll go with sine. Let's put that over here. So x divided by 14 is going to be sine of theta. And then we take our derivatives and we get 1/14 dx is equal to cosine of theta d theta. Then we just replace stuff. One thing to notice is that the 1/14 out in front can't this 1/14 times dx, that's dx over 14. You could just take that all the way and write it as cosine of theta d theta. Everyone following that? And then in the numerator, we solve that for x. X is 14 sine. And then we have to square it because that's squared, so we get 196 multiplied by sine squared. All right, so there's the substitution. Any part of that you aren't 100% sure on. So the yellow got replaced with sine of theta. I'm sorry. The yellow got replaced with, there's 1/14 dx. That got replaced with cosine of theta. So there's the yellow, 1/14 dx. 1/14 dx, that all becomes cosine theta d theta. X squared, we isolate x here, square both sides, we get 196 sine squared. Denominator, 1 minus sine squared. 1 minus sine squared in that square root.
We take out 196 again?
Yep. We shall. And what does the square, what is simplifies inside the square root? 1 minus sine squared becomes cosine squared, square root of cosine squared, cosine. Technically it should be absolute value of cosine, but they're not giving us any information about the domain, so we can just kind of ignore it.
Same as for your exam, you can just ignore that.
Yeah, I'm not going to ask you to put an absolute value. No.
Extra credit if we did. Just kidding.
Well, then you're not going to be able to finish the problem, most likely.
I don't know, because you've got to correct the business.
Yeah, because then you're going to be integrating a piecewise function, and integrating a piecewise function can get messy. And we're just going to assume the domains line up how they should to make things simple. And then these cosines cancel. So then we have sine squared, and we have to do the power reduction. So power reduction of sine squared, 196. We're going to do 1/2. 1/2, so the half factors out. And then what's left? 1 minus cosine 2 theta. Great. Now we're ready to integrate. So we're going to get 98, multiply. Integral of 1 is just theta. How about the integral of cosine 2 theta?
Sine 2 theta over 2.
Yep, sine 2 theta over 2. Perfect. Plus c. Now we need to use an identity. Sine of 2 theta is equal to
2 sine theta cosine theta.
2 sine theta cosine theta. And do you see that there's a 2 in the numerator now that's going to cancel with the 2 in the denominator? So this sine 2 theta becomes this. That 2 and that 2 are going to cancel. So we will end up with 98 times theta minus sine theta cosine theta plus c. Now we've got to go back to our original. Sine is equal to x over 14. So sine of theta is x over 14. Now we're going to build a triangle as if it's in quadrant 1 of the unit circle. We want sine of theta to be x over 14. Sine is opposite over hypotenuse. So we want opposite over hypotenuse to be that. So opposite is here. Hypotenuse is there. Pythagorean theorem. This is going to be square root of the hypotenuse squared minus that leg squared. And usually that's going to match something in the original problem exactly, or at least really close. Constant multiplier maybe could be off. So, any questions up to that point? We're going to see where everything is coming from. Theta, we come here, we take the inverse trig function of the constant.
Yeah.
So that's going to be 98 multiplied by inverse sine of x divided by 14 minus sine of theta is x over 14. Cosine of theta, we look at the triangle. Cosine is adjacent over hypotenuse. Square root of 14. The square root of 196 minus x squared, all divided by 14 plus c. So we have 98 inverse sine x over 14. Oh, and then there's some simplification that can happen here. I'll put the plus c. We're going to have x square root 196 minus x squared. So 14 times 14 is 196, so to me it looks like I'm seeing 1/2 out in front. Hopefully that's right. Everybody agree? 98 times 2 is 196, so we get half. Calculators are never wrong.
Yes.
Use substitution is never wrong.
It's funny, when the first TI graphing calculators came out, we found, I was in grad school when they came out, like the TI-80, I think it's called TI-81. And we found, even all the way up through the TI-85, we found errors on those calculators. TI-81, TI-82, and then TI-85.
And then they went.
Now
back
there's
to
no
82,
errors,
84.
but the first few years there was errors coming out of Texas Instruments. Not big errors, but small ones. Every once in a while.
Like what?
But now they're perfect.
Now they're perfect. Now they're perfect. That's a good company to work for.
We're just too busy making weapons.
Yeah, they make the javelin system.
You're the javelin missile system.
Gotta be precise.
No way they make
No,
that.
deadass. Texas Instruments created the javelin missile
Oh my
system.
god.
Calculators is just their side gig.
Yeah.
That's like their face to the public.
So instead they make anti-tank missiles.
Anti-everything.
They do all, they do all sorts of things.
That would be interesting.
Okay, how about this one? When we see it, the clue that you should think about trigonometric substitution is if you have a sum or a difference of squares. Difference of squares here, so we're going to use trig sub, sine, secant, or tangent. Secant? So if it's a positive, we know we're going tangent.
Yep.
Tangent, positive. So it's got to be sine or secant. So we ask ourselves, is secant squared minus 1 the identity, or is sine squared minus 1 the identity? Secant squared minus 1 is the identity. When we look here, secant squared minus 1 is tangent squared. That's the identity.
Also, they give us a domain.
And they give us a domain. Here they give us a domain. Yeah. They don't always do it, but.
They always do it for secant. Oh, yeah.
Oh, they always do for secant.
Yeah.
Good. Secant's the weird one.
Yeah.
If you look in different books will have different inverse secants, which is so annoying. So remember that when you create an inverse trig function, you're basing it on the restricted trig function. So for example, when you build inverse cosine, you look at the restricted cosine. So that's cosine. The restricted cosine is the biggest piece of it that's 1-to-1. So when you're doing the restricted cosine, this is what almost everyone is going to use for the restricted cosine, going from 0 right here over to pi. So almost everybody's going to do that for the restricted cosine. Now if you start looking at secant, secant has vertical asymptotes wherever cosine is 0. So here is what the first period of secant looks like that. So we want the largest piece of this, which is 1-to-1. Now in my mind, the natural thing is to use the same domain as we used for the restricted cosine. Right? So restrict secant with the same exact interval. And that's what most books do these days. But some books will be total contrarians, and they will pick this piece right here and this piece right here, only so that when you take the derivative, you don't have to deal with the absolute value. Right? You've seen in our notes here, when you do this integral, you have the absolute value on the where is the integral? You're going to see an absolute value on, when you differentiate inverse secant, yeah, I'm not seeing it anywhere. You'll see an absolute value on there. And if you do that very strange, in my opinion, restriction, you don't have to deal with that absolute value. So the thing that you'll see is that the derivative of inverse secant, when you take that derivative, you're going to get 1 over absolute value of x times square root. This is what you get if you use the one that I first showed you, that one. Because if you think about these two sides, isn't the slope of the tangent for both of those always positive? And if you pick this one and this one, isn't that derivative always positive? Right, the slope of the tangent is always positive. So that's why they put the absolute value there. And that's why if you pick the weird one, you don't need that absolute value. Because if x is negative, it'll all work out fine. But then it's just weird. So anyway.
On your exam, are you going to include domain?
I'm not going to give you anything tricky to deal with in terms of domains. It's kind of beyond. It's too much subtlety to deal with.
Okay.
Okay, so we're going to pull out the 400. We want a difference of squares with a 1, so we factor out the 400. It's in the bottom, in the denominator. So what is the exponent that's coming along as it moves out to the front?
3/2.
3/2 is the exponent, so if you pull something out of this quantity that has a 3/2 power, that power comes along. All right, so then let's see what's left. Inside here, there's no 400 with the x squared, so if you have to, you can imagine doing that. The 400 that you're pulling out is that one and that one. There's still a 400 in the bottom, so we make that x divided by 20, quantity squared, minus 1, all to the 3/2 power. And now we can use our trig sub with secant. So trig sub with secant, we're going to go x divided by 20. That's going to be secant of theta. Take the derivative of both sides. We get 1/20th dx is equal to sec theta tan theta d theta. And that gives us everything we need for substitution. Out in front, 400 to the 3/2. The half power is a square root. Square root of 400 is 20, so we're going to have 20 cubed in the denominator here. Dx in the numerator is 20 multiplied by secant tangent. So that's the dx. And then in the denominator, we're going to have secant squared minus 1 inside these parentheses. Raised to the 3/2 power. Any issues or questions on separating that out like that, substituting? That makes sense to everyone? Okay, secant squared minus 1. Tangent squared. Oh, one of those 20s can go away, right? So we're going to have 20 squared in the outside. And let's see, where are we at? Secant squared minus 1 is tan squared. Okay. So secant tangent in the top. Tan squared to the 3/2. And what's tan squared to the 3/2? Yep. So that's going to be tan to the 3rd. And doesn't one of those then cancel with the tangent in the top? So we get tangent squared theta, theta. All right, so if secant is to an even power, we have something to do. If tangent is to an odd power, we have something to do. That's not the case here. So that means Pythagorean identity, change everything to sines and cosines, one of those two things. If this square was in the numerator, I'd be more inclined to go Pythagorean theorem and then distribute something. But that doesn't seem to make sense here, so converting to sines and cosines. If we convert this tan squared to secant squared minus 1, then we have a denominator that's becoming multi-termed, which is always bad. It's always easier if the denominator is a single term, because then you can distribute it. So let's go sine and cosine here. So sine and cosine, we will end up with secant is 1 over cosine. Tangent squared is sine squared over cosine squared, but we're dividing, so we're going to do this. One of the cosines will cancel. So we'll end up with 1 over 400 integral of cosine over sine squared. And now what?
Substitution.
With u equal?
Sine.
Perfect. Because derivative of sine is cosine, and that's what's in the numerator. Everyone follow? So if we let u be sine, cosine's to an odd power. So you can imagine pulling it off and converting the leftovers. But there are no leftovers. So we don't have to do any conversion. We can just jump straight to u substitution. We've already done trig substitution. Now let's just do u substitution. So if u equals sine of theta, du is cosine of theta d theta. So we will have 1 over 400 times u to the negative 2 du. Integrate. So we add 1, get negative 1, divide by negative 1. So we're going to have that times 1 over u plus c. And then we have to back substitute. So we're going to have negative 1 over 400 times 1 over sine of theta, which we could write as cosecant of theta, plus c. Say again?
So we can rewrite that as negative cosecant theta over 400.
Yes, absolutely. Now we've gone from u back to theta, but we need to go from theta back to x. So now we've got to create our triangle. So secant of theta is x over 20. So let's see. Secant of theta is x over 20. So we're going to build our triangle again. You always build it as if it's sitting in quadrant 1. Secant is the hypotenuse over the adjacent. So this is where we're starting, hypotenuse over adjacent. Then we'll figure out the missing side, which will be square root of x squared minus 400. That allows us to rewrite this as, let's see, cosecant is hypotenuse over opposite. So we're going to have negative 1 over 400 multiplied by hypotenuse over opposite. Plus c. Woo, doozy. And we see that domain issue come up again. If x is not bigger than 20, then we have the square root of the negative.
Would you want us to combine it at the very end, or is it fine to leave it just?
It's fine to leave it like that. There's not a lot of combining to do. You could just put that 400 in the bottom. That's all you could do. Which you could write it that way too. Yeah. Ooh.
Only 15 questions? Well, how many, are they multiple parts by any chance? Any of them?
Maybe. All right, let's see.
15 questions, A through Z.
A through Z. A through Z times 15. What's 15 times 26? A number. An integer.
I'm going to do calculus now.
All right, let's see. So, I feel like we should definitely do some improper integration. Let's not do this trig sub. Let's pause on that and let's do some improper integration.
But that would be a tangent.
This one would be a tangent, yes. We can come back to it if we have time, but I definitely want to do some review on improper
We
integration.
get at least one partial fraction difference.
PFD?
Or, yeah.
Like an irreducible one.
Yeah, let's do one of the, yeah, let's do that. Yeah. Okay, so if the denominator is not factored, you have to factor the denominator first. This one already has the denominator factored. So this tells us that we are going to try to rewrite the integrand here with partial fractions. So this has two factors in the bottom. One that is linear, and the numerator for a linear is always a constant. If this said x squared in front, it's still linear, and you would have an a over x plus a b over x squared if it was to the power of 2. Okay, and then for our irreducible quadratic, for an irreducible quadratic, the numerator is always linear. So the numerator is always 1 less in power. So you're creating a proper fraction, the biggest possible numerator that keeps it as a proper fraction. So we put a linear over a quadratic. So there is our decomp right there. So now we have to solve for a. Why did I use D? When there's no C. Right. Like there's a big old gap there. Let's go with C. Let's stay in order.
Remember your plus D, guys.
Plus D. Oh man. Okay. So now we multiply both sides by the denominator on the left, and that's going to create this equation. Now we have a couple of choices here. If we want to use the traditional method, let's see, what's canceling? Not the x. Okay. We can multiply it all out and use the traditional method. We could use one convenient value and then rewrite it.
Do traditional, it's easy.
Okay, let's go with the traditional method. So it's going to be ax squared plus 25a. So we're just going to expand everything here. We've got that. Now we're ready to build our system. So we know that we need 3 equations because we have 3 unknowns, a, b, and c. A, b, and c. So on the left, the coefficient of x squared is 0. If you want to write it in, you can. So on the left, we have 0x squared. On the right, we look at all the x squared terms and we pluck off the coefficients. I see an a plus b. On the left, I see the coefficient of x as a 1. On the right, I look for all the x's. All I see is c. On the left, the constant is 1. On the right, the constant, any term that doesn't have an x in it, just 1, 25a. And this tells us everything we need to know. So we have that a is 1/25. If a is 1/25, b is negative 1/25. And of course, c is 1. So there are the 3 constants. Anyone have trouble with the equation? Solving for a, b, and c? Does that all make good sense? All right, let's create our new integral then. So we'll call the integral whatever we want to call it. I'll call it omega. So the integral, we're going back to the beginning. This is going to be the integral of a divided by x. So 1/25 divided by x plus bx plus c. So let's be careful here. So this is all in the numerator, minus 1/25 x plus c. All divided by x squared plus 25. Minus dx. Okay, the very first one, that one's pretty easy, right? So that first one is just a natural log. So we have 1/25 ln absolute value of x. Second one, we need to split the fraction. So that x squared plus 25 gets used twice. It's going to go into the first term and into the second term. So it's going to be, I'm going to break this into 2 integrals. So integral of this and integral of that. We're splitting the fraction, splitting the integral. So it's going to be minus 1/25 integral of dx x dx divided by x squared plus 25. So that's this one. And then the one on the right is plus the integral of 1 dx divided by x squared plus 25. Everyone following that? So we're splitting the fraction. That, and then the 1 over the denominator. This first integral, what form is it almost in? Log form. We're going to multiply the numerator by 2, multiply the denominator by 2. The derivative of x squared plus 25 is 2x. So we need a 2 there so that the derivative of the bottom is the top. The one on the right is going to be a tangent inverse. So let's get to that. So here we'll have 1/25th natural log absolute x minus, so out in front we have 1/50th natural log absolute value. We don't need absolute value here because this quantity x squared plus 25 is never negative. This is an arctan here. I'll factor out the 25. Factoring out the 25 is going to leave us with x divided by 5, quantity squared plus 1. That'll be arctan of x over 5. So all that stuff's going to come down. We're going to have plus 1/25th. We're going to need a reverse chain rule, so I'll leave a little gap. We'll have an arctangent of x divided by 5. And what goes in the gap for reverse chain rule? 5. Yeah, then we just have our final answer. So that plus 1/5 times arctangent of x over 5. Plus c. All right, any question there?
Would you accept the dashes in our answer?
I would accept dashes if it's nice and neat and I can follow them. Totally fine. Yeah, that's fine. Dashes are good.
I love dash.
Dashes are good. Save on some writing. I need to roll. All right, improper integral. When you see infinity as a limit of integration, then you know it's improper. So the next word out of your pen or pencil should be lim. That should be the next word out of your pen. Limit. And so in this case, it's the limit as, we can use a B or an A, whatever you want. See, this book will usually use a B for this type of improper integral. So we're going from 11 to B. That's x to the negative 1/2 times dx. So in your mind, you're thinking about a function that's approaching the x-axis, and we've got, so out here at 11, let's just go way out here at 11. If we plugged in 11, I don't know where we're at exactly, but we have this kind of situation.
That's pretty slow.
It's very slow. It's going to the x-axis very slowly. 1 over the square root of x is certainly going to 0. 1 over the square root of x is going to 0, so it's approaching the x-axis asymptotically. But we've seen that our threshold is 1, x to the 1 in the denominator. If the power is less than 1 in the denominator, we're going to get a divergence on the horizontal tail. So let's see. Let's confirm. So 11 to b, we're imagining b is just some random point out here. And 11 to b, we are finding this definite integral. And we're going to find that definite integral as a function of b. And then we just let b go to infinity. Once we have our function of b, take the limit as b goes to infinity and evaluate. So let's see. So here we're going to get x to the positive 1/2 divided by 1/2 is multiplication by 2 from 11 to b. I'll factor the 2 out to the front, so this is going to be 2 limit square root of b minus square root 11 as b goes to infinity. And that limit is
Divergent.
all you can eat. Infinity. All right. So that means that the area here is not finite, it's infinite. You would also say the integral diverges. So all you have to do is write this down though, you're done. All right, another improper. Any questions on it? So improper integration means we're trying to find the area of an unbounded region. So this region here is unbounded. You can't put a circle around it.
What about a vertical one?
Yeah, we'll do a vertical. Should we do a vertical one right now? Let's do a vertical one. So vertically unbounded is not as obvious because you don't see the limit of infinity or minus infinity. But what we notice is that this is not a definite integral because this denominator is not defined at 7. So we've got an asymptote at 7. So it's vertically unbounded, this region.
The board says it evaluate the following indefinite integral. Am I insane or is that definite? Like improper?
That should say improper. That should say improper. Thank you. Good catch. That should say improper. Improper. So it's not definite. It's also not indefinite. So yeah, that is improper. Improper. Okay, so here, same thing. Once we recognize that it's improper, we want to take a limit. And we're going to take a limit as x is approaching 7, because 7's the bad point. We want to make sure that we're staying in the interval. The interval is from 7 to 8. So 7, 8. So when we're coming over to 7, are we coming from the right or the left?
Right.
We are coming from the right. Everyone following that? If we're looking at our interval, 7 is here, 8 is here. We need to stay in this interval. So that means that we're approaching 7 from the right-hand side. So it is a one-sided limit. And so this, oh, and I used an X. Usually this book will use a C for these vertical ones. So we're going to go from C to 8. And let's go ahead and move that quantity up to the numerator. So x minus 7 to the negative 5/4 power dx. So do not forget the limit symbol.
How much will you talk if we forget the limit symbol?
At least one. Maybe more. Maybe more. All right, so x minus 7, it's linear. X minus 7 is linear, so we're going to use the power rule followed by reverse chain rule. But we see reverse chain rule is kind of insignificant because the derivative is 1. So we're going to add 1 to the exponent here and get negative 1/4. Dividing by negative 1/4 means multiplying by negative 4. That will be from C to 8. This is going to be limit. Let's pull out the -4. Get the constant out of the way. So we're going to have 8 minus 7, which is 1. 1 raised to any power is just 1, minus the quantity c minus 7. So the -1/4, I'm going to make it a positive 1/4 and put it in the denominator. It's always easier when there's no negative exponents. We're taking this limit as c goes to 7 from the right. So if 7 is being approached from the right, c minus 7 is always positive. And that we can then take the 4th root of that. If we were approaching 7 from the left, this would not be defined. You can't take the 4th root of a negative. All right, so this denominator is going to 0. And it's going to 0, but it's always positive. So it's going into 0 from the right. E. Approaches 0 from the right. Everyone okay with that? It's going to 0. It's always positive, so it's getting smaller and smaller and smaller, but it's positive always. So what does that mean? What is 1 over a number that's approaching 0? 1 over a number approaching 0 must go to infinity. So this part here is going to approach infinity. This whole thing here, that's approaching infinity. So 1 minus infinity is approaching negative infinity. So this whole thing is going to negative infinity, which means the overall limit is
Infinite.
positive infinity because we have a negative times a negative. So this will be positive infinity, aka just infinity. Now let's go with our intuition for a minute. So we had a vertical asymptote, so a vertically unbounded region, and we have seen that vertically unbounded regions have finite area when the power in the denominator is less than 1. Right? Power in the denominator less than 1 has infinite horizontal, finite vertical. Okay, let's do one more improper. So find the volume of the solid, or state that it does not exist. The region bounded by f of x equals x to the -5, and the x-axis on the interval 2 to infinity is rotated around the x-axis. So we have a function that's approaching the x-axis very fast. So it's approaching very, very fast. And we're going to look from 2 to infinity. And so from 2 to infinity, we are dealing with all of that. We are rotating around the x-axis. We're going to use some disks here. So we're going to choose a random vertical element. Rotate it around the x-axis. So we are using disks. The area of a disk is pi times the radius squared. What is the radius in this case?
X to the -5.
Mm-hmm. So the radius is the height of that purple element. Because that thing's being rotated around the x-axis, creating a disk of radius x to the -5. And then we're squaring it. So there's pi r squared. So this will be pi times x to the -10. So that's the area. So those disks are getting very small very quickly. And the volume will be the integral of pi x to the negative 10 dx. We integrate area to get volume. We're going from 2 to infinity. So here is what our improper integral would look like. The second we start to evaluate an improper integral, the first thing we write down is limit. Limit as b goes to infinity.
Should we take out a constant now too?
And you can pull out the constant if you want, absolutely. Yep, you can pull that out. Whoops, I put an infinity up there, but we're going to go to b. So there we have it. So improper integrals are always evaluated with limits. We can integrate here. We can factor that pi all the way to the front if we want. Add 1 to the exponent and get negative 9 divided by negative 9 from 2 to b. So let's factor out the negative pi ninths so that we're just dealing with the minimal part of that quantity. We're going to b to the negative 9, which is 1 over b to the 9, minus 2 to the negative 9, which is 1 over 2 to the positive 9. And this limit is as b goes to infinity. So, what does 1 over b to the 9th go to? That's going to go to 0. So as x is going to infinity, as b is going to infinity, this is going to go to 0. So our overall limit then is negative pi ninths multiplied by negative 1 over 2 to the 9th. So this is going to be positive pi all divided by 9 multiplied by 2 to the 9th. That is our volume. So that volume is finite.
We don't have to simplify the
2 to the 9th. What is 2 to the 9th?
512.
2 to the 9th is only 512? No.
Times 1 is 4,608.
4,608?
Yes.
Yeah. That's easy enough to simplify.
It's on card.
Easy enough to simplify.
With a minus sign somewhere.
Minus sign, what?
Never mind, your shoulder was covering it. I guess.
Minus. No minus. No minus volume.
Yeah. Negative volume.
Negative volume. 1 mole. Okay, so let's go to some DEs. Let's go to the last couple here, some separables. So we want to separate here, and we've seen earlier camping.
Yeah.
Where?
Up in Empire.
Oh, nice.
I'm betting he's not going to make it up the Full Wheel Trail.
Hmm.
He was trying to take my truck, and I was like, no.
Not worth it.
I don't know if I trust him with that truck 4-wheeling because he hasn't 4-wheeled before.
That seems like a bad idea to give your truck to someone who doesn't know what they're doing.
I agree.
Dustin, would you give your truck to someone that doesn't know what they're doing?
I wouldn't give my truck to someone who does, no.
Especially 4-wheeling. Okay, so
It's a stick shift too.
everybody agree on this separation?
Which kind of makes sense.
Because this is a subtraction in the numerator exponent, we can make that e to the x and e to the negative x. When we multiply, we add the exponent, so we'll get x minus y. And then we can move the y's to the left by multiplying both sides by e to the y, move the dx to the right. And now we integrate both sides. So on the left, the integral of e to the y is itself. So So integral of an exponential is always itself, and then you divide by the derivative of the exponent, but that's only 1 in this case, so e to the x plus c. Okay, so now this is, on the test, you'll be asked to solve for your dependent variable if you can. So this right now is called an implicit solution. We have not isolated y, so we want to isolate y. So we're going to take the natural log of both sides, and this is our general explicit solution. So that is our general explicit solution. Now we were given this initial value right here, so now we want to plug that in and figure out what the c value has to be. So this gives us an infinite collection of parallel curves. We want to pick the one that satisfies that condition.
I noticed when we're working these, we box a couple different answers. On the exam, can we do the same thing? Star the final one or something?
Yeah, because this is going to be a two-part thing. Find the general,
Oh, okay.
find the explicit general, and then find the particular.
Okay.
So now we'll find the particular. We know that y of 0 is ln 3. So when we plug in 0, we're going to get ln of 3. So we can exponentiate both sides. So c is 2. So this tells us, therefore, the particular solution we're looking for is natural log of e to the x plus 2.
Do we have to include the therefore sign?
No. Any part of that you're not sure about? Yeah.
Can I plug in the initial variable into the equation?
Right here?
Yeah, into there.
Yeah, you can. You can plug it in here and solve for c. The only issue is that you need to find your general explicit, and these c's might not be the same. In this case, they are the same because we didn't do anything. So you could plug into this and you'd get the same value of c.
Okay.
100%. Yeah. Sometimes those c's don't match, so if we
Yeah.
combine them with stuff. Yeah.
Just because this is squared.
Now let's look at this last one.
There's no 3x's.
So this one, same idea. We want to separate it. The first thing we want to do is make sure we're using differential notation instead of prime notation. So we're going to do that. And then we're going to move the y's to the left. So we're going to have that. And we're going to put the dt to the right. So we have that. And then we can integrate both sides. The left with respect to y, the right with respect to t. The left side becomes natural log absolute y plus 15. The right becomes 1/7. So we have to use reverse chain rule. Or you could do this. You could do a 7 here and a 1/7 out in front. However you want to think about it. So this is going to be 1/7 natural log absolute 7t plus 50 plus c. Is everyone okay up to that moment? So we want to, now we want to get, so this is the one that's got a little bit of trickiness with the absolute value. We're going to raise, we're going to exponentiate both sides. and we cannot take away the absolute value right now, the right-hand side is always positive. But what we can do is break off this c, and we can separate this and make it c e to the 1/7 natural log absolute 7t plus 50. So once we get here, now we can take away that absolute value because there's this arbitrary constant on the right which we can mash a sign into. So this is going to be y equals, so the absolute value goes away. We get this. And then subtract 15. So that is our explicit general solution. And then we would plug in the initial value and finish it off to get our particular explicit solution, which I'll write on the board in a minute. All right. So I'll check email frequently. I'll have the worksheets back to you in a couple hours so you can finish those off for Thursday night. Anything comes up, you can use the Ask My Instructor button or shoot me an email, and I'll see you Thursday. I'll be in the Math Center tomorrow from 9 to noon if you're around and want to do math. If not, I will see you on Thursday. Good luck studying. Carry on.